after this lunch break. So I hope everyone had a good lunch and is ready for the coming 8 presentations, which we have in our session on materials characterization for AM materials related to biomedical applications. So a broad range of topics coming along in the next 1.5 hours. My name is Jürgen Stampfl. I'm professor here at TU Wien for materials and additive manufacturing, and will be heading this session. Also, some encouragement from my side to look at the uploaded presentations. I just briefly checked the number of views of most of our coming presentations, so they haven't been looked at very intensively. There are some really excellent talks there, so make use of this opportunity to also look at the original presentation and not only at the short presentations which we're going to hear now. That's just a few words to start with, but without delay, we should jump into the presentations. And the first one is given by Anna-Lea Kutsch. She's a PhD student in my group and working on additive manufacturing of silicon nitride. And her talk is entitled Investigations on the Rheology and Deagglomeration of Digital Light Processing based wet polymerization of silicon nitride slurries. Long title, interesting topic, and Anna-Lea, so please try to share your screen and give us a couple of minutes insight into your work, and afterwards we'll hopefully get an intense and interesting discussion.
Yes, I will talk about the optimization of rheological slurries for digital light processing today. And first of all, there are a lot of people who need bone implants, and reasons for that can be different. But one really promising material for bone implants is silicon nitride, because it is biocompatible and may lead to osseointegration. And one process which is promising to process silicon nitride is by digital light processing, which we can see here on the right-hand side. And there we build out our parts layer by layer due to the energy of light. So the question arises, how can we process silicon nitride? And therefore, first of all, we need a slurry, which is printable and does not have agglomerates and is stable in vivo. Usually ceramic particles tend to agglomerate in slurries, so we use dispersing additives in our slurry to prevent this and to stabilize our slurry. And therefore, in a pre-study, we investigated different dispersing additives, and we found that the dispersing additive D2 seemed to work most promising in our slurry. So we investigated it more closely. And here on the left-hand side, you can see the viscosity of our slurries, which were prepared with different amounts of dispersing additives. So we see when we increase the amount of dispersing additive, the viscosity of our slurry decreases. And then we also wanted to identify if the slurries with a different amount of dispersing additive is stable. So we performed frequency sweeps of the slurries. And here in the middle, we can see a slurry which was prepared with 1.25% of D2. And on the right-hand side, we see a slurry which was prepared with 1.58% of D2. And when we look at the lower frequencies, we see that for using 1.258% of D2, it seemed that this slurry was stable, as the storage modulus is above the loss modulus, and it is above 10 Pascal, which is not the case for the slurry with 1.5% of D2. And this is the reason why we concluded that for our slurry, the optimal amount of dispersing additive is 1.258% when considering the viscosity and the stability. So we used this amount of dispersing additive to print samples, which was possible, as we can see here. We see the building platform, and also it was possible to debind samples with this slurry. And with that, I would like to thank you for your attention, and also to the project partners and to the group.
Thanks, Anna-Lea. So we have time for a couple of questions. I will check the chat, and if someone is raising his hand. So far, I don't see anyone. So maybe a comment from my side. Could you somehow explain why silicon nitride is quite challenging for lithography-based additive manufacturing? So we have experience with quite a few different ceramics, and silicon nitride is one of the most difficult ones.
Yeah, like it has a really high refractive index, and it absorbs light. And so we don't have a high penetration depth of the light in the slurry, which we need when we want to print with high layer height, and also when we want to get the adhesion of the layers.
Yeah, and penetration depth, how is that, also by which properties of the material is that determined?
Like when we look at oxide ceramics, there we have there the refractive index is important for the penetration depth, as there, if the refractive index of the ceramics and the slurry is really different, then it leads to scattering of the light. And yeah, this is influenced, and we can, and for our case, as the silicon nitride absorbs the light, we don't get this high penetration depth. We only get like around 60 micrometers.
Thanks. There's a question from Luca Bellotti, please.
Yeah. Hi. Thank you for the maybe a more general question. So, like about the ceramic that you're studying, why? What is the application that you have in mind with these particular ceramics? And what would be the advantages of using the silicon nitride compared to? Okay, the advantages is fine, but like, what's the particular application that you have in mind?
Like there are studies on bone implants where they use silicon nitride, and it has the advantage that it also leads to bacterial and viral resistance, but in the same time, it is accepted by the human body, and also we have an ingrowth into the material. So yeah, therefore it is really promising.
Yeah, okay, yeah, I think, yeah, just sorry, it may be a very general question. It's just because I'm really like, I always study more metal, so it's but it is interesting anyway. Thank you.
Well, it's a very valid question, because why take such a difficult to process material if there would be easier choices like alumina or zirconia? But silicon nitride has definitely a few properties which are very appealing. So looking into the chat, and it seems that we don't have any further questions here. Thanks to Anna-Lea once more. And again, please also look at the complete video presentations on YouTube, where you will find a lot of additional information and insights into our topics. But first, thanks to Anna-Lea. And we might head over to the next presentation, which is given by Alexander Berndt. I just saw him on the participant list. Yeah, here he is.
Yeah.
So he's working at the Fachhochschule Kärnten in the south of Austria, and he's going to talk about additive manufacturing of continuous carbon fiber tubes and experimental investigation of the energy absorption of such structures, also related to biomedical applications, also probably in a very different field than silicon nitride, but we are looking forward to your short presentation, a couple of minutes, 3 to 5 minutes, and then hopefully jump into a fruitful discussion. So please share your desktop, and the stage is yours.
Thank you very much for your introduction, and try to share my screen then. And then we can start to go into the short presentation. Yeah. Welcome to my presentation. Again, my name is Alexander Berndt, and I'm working at the Fachhochschule in Kärnten as a junior researcher, and also doing my PhD in with the Montan University in Leoben. And today I'm going to talk shortly about the additive manufacturing of continuous carbon fiber tubes and their experimental testing. To give again a short overview, we started with our ideas and an aim of a force-dependent path design for fiber orientation. So we needed new printing strategies for high-performance composites, and therefore an implementation of a fourth axis. We wanted to use, or we used the material from Markforged, which is continuous carbon fiber material. We also used the Markforged Mark II printer, which we kind of opened, and so we could use our own or open source software for that. And therefore, we sliced our specimen in the Aura software and designed 2D designs to print these 3D structures. To show you again shortly, this is the first layer printed on our modular fourth axis. So it is plus 30-degree fiber angle. Then the second layer again with minus 30-degree fiber angle, and after that there is a layer with 0-degree fiber angle. Then again one with 0 degree 3 times, and after that again 30, plus 30, and minus 30-degree fiber angle. After we manufactured those 25 specimens with different layups of fiber angles from 15 degrees up to 75 degrees, we tested them under quasi-static loading conditions. So we wanted to see, or we wanted to determine the specific energy absorption capability of those tubes. So we measured and weighed those tubes and then tested them under quasi-static loading conditions with 10 millimeters per minute as speed. And then we calculated the results of the different specimens we made. So the 15-degree fiber angle specimen had the highest amount of specific energy absorption capability, around 65 kilojoules per kilogram, compared to conventional winded tubes, which have around 90 kilojoules per kilogram. We came quite close. So we were quite happy with our results. And yeah, I'm ready to hear your questions, and thank you for your attention.
Yeah, thank you, Mr. Berndt, for this short introduction into a very interesting topic regarding fiber reinforced materials. I see one question from Luca Bellotti, please.
Hi, thanks for the presentation. It's very interesting to see the effect of these this fiber angle. I'm just wondering, especially on this fiber angle plot that you have. Yeah. I see that you seem to have a much larger deviation for your lower angle, your lower fiber angles. Is
Yeah.
this is this something systematic that you see, that you identify, or
It
is
is,
just
it is actually based on the manufacturing process itself. Yeah, we had quite difficulties to print it in these narrow kind of angles, and the layers itself had quite some impurities and voids in there. So it took quite some time to get them printed actually, and yeah, as you said, the derivation is quite high in these kind of angles or fiber angles. Yeah.
Yeah. Okay. Yeah. No, because it's interesting, because it seems like as you go for 15, you have a very high deviation, but for 75 you have a very small deviation. So it's just like how many samples did you test?
For each fiber angle, 5.
Okay.
Yeah.
Wow. Yeah, it's interesting to see. Maybe something to like in the process when you're making like a process mechanical property relationship. Maybe something to investigate a bit further.
Yeah, exactly. Yeah.
But interesting. Thanks.
Yeah.
I also have 2 or 3 questions actually. One is more practical, related to software. I mean, if we talk about additive manufacturing, the classical method is to do slicing and then somehow send over these slices to the printer. So your approach is now quite different, because you need a different way of manufacturing these things. So if you look into some making parts in the long run, do you see some issues with software related? Also, how would you somehow not slice, but how would you transport your geometries to the machine in the long run?
The problem is, if you really use, for instance, 5-axis for printing, then there is not a real, or at the moment, no conventional slicer, which is able to slice your parts in a way which can, or how the 5-axis machine can produce them actually, or at the moment. So that's why we chose to unwind these 3D structures into a 2D structure to slice them in our printer. So at the moment, it is quite difficult, I think, to really print in a 3-dimensional way with, for instance, a 4-axis or 5-axis machine, because of the lack of this kind of slicer software. And I think, I'm not sure if Clarissa Becker today talked about how to use such optimization structures, but it might be. So we have some ideas, but we didn't actually test them at the moment.
That's what I was expecting. So there are some challenges.
Yeah.
And probably you need some more CAD or CNC-based approach for rating your machines, and these conventional layer-wise software packages, they will lead you into trouble.
We are currently working on that actually. With Rhino and Grasshopper, for instance, is one approach to use this kind of software.
Okay, great. There's another question in the chat from Lars van Munster. What's the minimum tube diameter or maximum tube length you can reasonably manufacture with this method?
Actually, we don't test that, but the tube length itself is, it is like the area of work surface from the Mark IV, Mark II printer. So I think we can go up to 200 and something millimeters in length, and the diameter depends on the 4th axis. If we make this kind of axis bigger, then I think we can go up to 100 millimeters in diameter. So actually it is, depends on the size of the printer.
Okay, great. There are no further questions, and we are perfectly in time, actually. So
Okay.
I thank Alexander Bernd once more.
Thank you.
Thanks a lot. And can directly switch to the next presentation, which is given by Martin Schwentenlein from Lithos. Is he here? I saw him. Someone. But at the moment, we are missing him, I would say. No. I don't see him in the participant list. Yeah, now we are a little bit challenging our schedule. What are we going to do here? Let's just give him a second. Maybe he's showing up. Because I don't want to, I saw the next author, but I don't want to mess up the schedule too much. Since I see Jan in our organizer in the list. So Jan, should we move forward the next presentation, or should we keep the time schedule? What do you suggest here? Oh, also no answer here, or maybe Filippo as co-organizer. No one answering. But I hope anyone can hear me, right? Because it's not. Can people hear me?
Yes, we can hear you.
Yes, we can. We can see you and we can hear you.
Okay, great. That's not the problem. Because I didn't get any response there. So neither Jan nor Filippo can help me out here. But I think we prefer to stick to the schedule because otherwise people get confused. I'm just checking. As Lars, you are here, right? So for the next presentation, I see him. Lars,
Yes, I'm here.
so you are here and you can hear me and we can hear you.
Okay, thank you.
But I suggest if I don't get recommendations from the organizers, then I think we stick to the schedule. So I still don't see Martin Schwentenwein anywhere. I will try to get a hold of him. So my recommendation, so we stick to the schedule. So anyone take a coffee. We have a couple of minutes coffee break, unwanted one. But otherwise we completely get out of synchronization. So please grab a coffee. I will also grab one. And then we just continue with our planned schedule and with the next presentation, which will then be given by Lars van Munster. So see you in 5 or 7 minutes. interesting presentation from the University of Leuven in Belgium, given by Lars van Munster. And he's going to talk about metals now. So we had ceramics and now switching ceramics and composites and now switching to metals. And his talk or his presentation is entitled Mechanical Behavior of Engineered Open Porous Titanium 6 Aluminum 4 Vanadium structures produced by laser powder bed fusion. So again, recommending to look into YouTube to everyone, but Lars will give us a short insight into his work right away, and then we have some time for discussion.
Okay, thank you, Chairperson, for the introduction. Can you hear me and see my slides?
We can hear you and we can see your slides. It's not in the presentation mode yet, but yeah, now it's in the presentation.
Okay. Thank you. So indeed, this research talked about titanium 6 aluminum 4 vanadium structures for dental applications, and we try to control the porosity inside these structures. A little bit on the background about these topics. The idea came from dental implants because many of these implants suffer from formation of a biological layer around the implant that leads to inflammation of the tissue, and in the end will lead to failure of the implant. And to prevent this, we would like to locally apply drugs, but the problem is trying to find a place to do this. So we thought of placing the drug reservoir inside of the implant, but then we need a way to get the drugs outside the implant again, and this we would like to do with controlled drug release. The question now is if we can find structures that are both strong enough to survive the forces during eating, as well as allowing for these microporous channels for the controlled drug release. So what we try to do is we achieve this by varying the laser powder bed fusion parameters, mainly the hedge spacing. By choosing this much larger than you would normally do, you get these pore channels. And by varying all parameters together with the hedge spacing, we got fully interconnected pore channels. And then we tested the mechanical parameters of these structures and tried to find an optimal set that would lead to both strong enough as well as interconnected pores. And this set was then tested, first of all, for its interconnectivity. And indeed, we found that it's possible to make a set that has fully interconnected pore channels. Secondly, for their quasi-static properties. And indeed, we found that we could make these interconnected channels strong enough for dental applications. And then finally, we tested them for their dynamic properties, especially fatigue under an inclination, because this is the most realistic situation when simulating the forces during eating. And this way, we found that after heat treating, it was indeed possible to make the structure survive the dynamic testing. Which brings me to the conclusion of my research. This was that the oversized hedge spacing strategy is indeed possible to use as a way of creating fully interconnected pore channel networks. And that these networks, the mechanical parameters of this network can be controlled by varying the process parameters. And then finally, we found that the fatigue behavior was promising for dental applications, but of course, further testing will be required to see if they will actually survive inside patients. I think that was a very short introduction about my topic.
Yeah, thanks a lot for this short but concise introduction into your topic. I'm looking into the participant list if someone is raising his hand. Yeah, there's one. I also have a couple of questions, but let's first Anton Duplessis ask his question.
Yes, thank you. Thanks for that. I've read some of this work recently, actually, I think in Additive Manufacturing Journal, potentially. So I just have a question for you. You're basically making single tracks with wide hatch spacing. Is there a concern about trapped powders not necessarily attached to the surfaces and removal of loose powders or powders becoming loose over time in usage? Can you comment on this?
Yes. So first of all, after production, removing the powders from the channels is indeed a challenge. Our samples were ultrasonically cleaned for 4 hours, and we were able to remove virtually all of the loose powder. And when you comment on this in use, in the eventual application, we envision filling these porous structure with silica, which is a mesoporous silica type that we will be using for the better controllability of the drug release. And this silica will then lock in place all powder particles that would remain inside the structures.
Okay, thank you.
I have one question related, so you didn't show that in your short presentation, but in the long presentation, the strength you calculated from the mastication forces, and you came to 500 megapascal, which for me is quite a lot, because usually in dentistry, the dentin itself has around 100 megapascal, which strength, which obviously is usually enough. And also most dental materials like composite, the light photopolymerizable composites or glass ceramics, they have much lower strength values. So don't you think you somehow that you put your target too high in this respect, and wouldn't it be enough to have much lower strength values?
Maybe indeed we based our quasi-static strength values on the worst case scenario we could find in literature, but for the dynamic stress values we used, I think 170 megapascal as a minimum load, which is much closer to the values you were referring to. And indeed, it might be that we slightly overestimated our strength, but the main importance was having a small port channel, small enough for the application, as well as full interconnectivity, and those two values were reached first, and only then we started looking into the strength, what could remain.
Mm-hmm. So you try to be on the very safe side somehow. Yeah.
Indeed.
Yeah. And also because we are talking about fracture mechanics a lot, did you also do fractography to see what's causing the failure of your material if it fails at some point?
Mm-hmm. We didn't yet do it on the inclined fatigue test, as we will try to do it after the silica infusion, which I was talking about, since we think that there might be slight changes in the way it fails once the pore channels are filled with the mesoporous material. But at this point, there was not done any fractography yet.
No. And last question from my side, because I don't see any from the audience so far. So you're also looking into drug release mechanisms, right, to prevent inflammation around the implant. Do you already have an idea how you would do that? So you have a really long-term or sufficiently long-term drug release from your porous structure into the surrounding tissue?
I cannot comment on the actual length of the tissues itself, but this research was actually based on previous research at our materials department, where they used similar material that was created by partially sintering cold compacted powder, and they found that structures with the same properties as the ones I designed could indeed be used for long-term drug release. Their main problem was that they could not do proper net shaping, and of course in LPBF we can do this. So this is the main advantage of this research, and if you would combine, and we think it might be possible to have a long-term drug release.
Okay. Yeah, still no further comments, but anyway, very interesting and very in-depth investigation of this very important biomedical material. So thanks once more to Lars for his presentation. I think we are quite well on time. I also got some hold of Martin Schwentenmein already. So I will try to convince him that we put him at the end if I try to communicate with him. So he's somehow around, but obviously something went wrong. But we stick to our schedule for the time being and switch to the next presentation, which will be given by Luca Bellotti. And he's going to talk about microstructural features of thick-walled 316L stainless steel produced by wire arc additive manufacturing. So please give us some idea about your work.
Okay, can you see my screen?
Yeah, we can hear you, see you, and also your laser pointer is alive, so everything
Perfect.
is perfect.
Perfect. So, well, thank you for the introduction. Actually, a quite different topic and different application compared to the previous presentations, because actually the focus of my work is not really on biomedical applications, but more on large-scale applications, marine and offshore. But anyway, we're just gonna this presentation is going to be more focused on the metallurgy of the part and some of the steps that we're trying to do to understand the application of wire additive manufacturing and from the metallurgical point of view, and improve the application of the method. So first of all, okay, let me just. Okay, yeah. So first of all, like wire additive manufacturing is basically it's one group of techniques that are based on the traditional welding processes that are very good candidates for manufacturing large components, exactly because they have high deposition and building rates. And because we're using them in an additive manner, it gives the possibility of making very complex parts and also to tailor the local microstructure. But exactly because we're using these fusion processes in a repetitive manner, we have a heterogeneous microstructure, which translates into anisotropic mechanical properties, which, depending on the application, is not necessarily a bad thing. But in order to be able to fully exploit the versatility of one, we need to really understand the relationship between the two. And when I mean understand the relationship between the two, not only in terms of structure, but also in terms of the process itself. So therefore, the goal of this work is actually to investigate the microstructure. So we're not going to be presenting any mechanical characterization today, but it's because we need to have a fundamental understanding and relate these to how we process the part. So we work with a austenitic stainless steel grade with actually a standard welding wire and also standard welding shooting gas. And we make a block sample, like a thicker wall. And then we investigated the microstructure. So if we take a look at the cross section, we see that the first thing is that, okay, we have a very coarse structure, very elongated, dominated by two traditional solidification mechanisms like epitaxial grow and competitive grow. But we also see that we have a gradient in the microstructure that closer to the base plate, we have a finer grain structure, but from the second layer on, you have a coarser structure. And this is because of the difference in the cooling rates. We didn't preheat anything. So from the second layer on, it's like you're depositing on a preheated material. But we also see that these grains are very oriented. So we can post-process these, and then we can do several different analyses. In this case, we were interested in seeing the repeatability and the spatial variability of this grain size and grain grow direction. And we see that we have a periodically repeating structure with regions in which we have very elongated grains and regions that the grains are less pronounced. And if we analyze a characteristic structure, which is actually a partial weld bead, which is a fusion zone, we see that part of these grains tend to grow like this. The purple grains here tend to grow perpendicular to the fusion interface, but the red grains tend to grow are in the overlapping region, which means that you have a band in which you promote unhindered competitive growth, and therefore you have very large grains, which results in very textured structures, and therefore you translates into anisotropic mechanical properties as well. And we did we also did some studies in terms of the spatial variability of phases and the phase fractions, and we see that there are local variations in the morphology of secondary phases, but the overall content does not significantly change. And as a main conclusion for the work is that, okay, one way that we can tailor the microstructure is by actually by controlling the fusion zone geometry, and based on and also the deposition strategy. So the way that you're stacking the parts, or your deposition strategy itself, combined with the fusion zone geometry plays, actually controls the microstructure and the mechanical properties of the part, and consequently, and potentially the mechanical properties of the part. And with these, I'd like to end my short summary, and thank you for your attention.
Yeah, thanks, Luca, for your insight into another very important process. Since there are no up-to-date questions, I have a couple of them. As a one simple question would be, did you make your machine yourself? Or is that a homemade wire arc manufacturing system?
No, actually, no. It was we went to we manufactured the samples at Ramlab, so the technological company in the port of Rotterdam in the Netherlands, and they were actually the first company to also manufacture the ship propeller, and it's so that they had expertise in terms of the of processing the material, and also the like they have their own online control of the heat input and printing strategies and that kind of stuff. But we had the input because we're more interested in the metallurgical point of view. So from the metallurgy point of view, so we really wanted to understand and relate the initially keep the printing strategy as simple as possible, making a thicker part so that we can actually come up with and then afterwards we move to something that is a bit more complex, which is something that we're investigating now, like relating process, microstructure, and mechanical properties.
And I mean, one of the main benefits of wire arc manufacturing is the substantially increased throughput compared to powder bed fusion typically. Can you somehow give an idea of how much kilogram per hour or whatever speed throughput unit you use? So where are we standing there when looking into wire arc manufacturing?
Well, it really depends on the like what type of application you're working on, but you can go up to 10 kilograms per hour is something that people already of the position rate. Building rate, of course, is a bit lower because you also have the interpass temperature that you need to cool down. You need to let the material cool down eventually. But I don't know if you're familiar with, if you saw there's a new company that is printing a rocket, Relativity. They're printing a full rocket on and I suppose they also like, as far as I know, they are not using any type of active cooling outside, but that if you use some type of external active cooling, for example, doing some compressed air or using some water cooled tables, which is the case that we did, you can increase the build rate by quite significantly. But then the challenge is that it's not a modular deposition anymore. It's very difficult to take it to the on-site. And one of the goals of WAM is also so that you can put the printer on site and just do some repairments and build a part on there, and then if you start having a lot of these add-ons, and depending on the size of the part, it becomes very challenging to do so. Because we're talking about meter-sized components.
And I mean, since we're mostly focusing on biomedical applications in this session, I mean, you didn't go into your YouTube presentation, but do you see some, also in terms of biomedical applications, where would you see the largest potential for wire arc manufacturing?
Well, in biomedical applications, you could think about, like, for example, heat implants. If you, it could be a potential application, for example, with titanium that you can use. But the issue is the disadvantage that WAM has is that it's not it's the surface quality is usually quite poor. Compared to laser-based processes. So you do need some post-processing anyway. And then, of course, because of hip implants, friction and wear are very, like the tribological characteristics are very important. So you do need to have a good surface finish. So it's inevitable that they're going to need some post-processing. But in terms of dental implants, as the previous presentation, I don't think WAM is the best technique for that, for sure.
You never know. I mean, I would guess that you have usually fewer problems with voids and defects compared to powder-based processes. I mean, especially in terms of fatigue and with more fracture mechanical aspects. I could imagine that wire arc manufacturing is not such a bad idea in quite a few cases.
Yeah, it's usually, you usually have like 99.8% of bulk material, so it's porosity is definitely less of an issue. But then there is the issue that the welding wires are developed for welding. So you do, and not necessarily for additive manufacturing. So one may think that it would be the same, but we do have a lot of these micro inclusions. So when we think about high cycle fatigue, maybe although people don't report that there's a significant impact, there's still the study of WAM. It's still relative in relative infancy. So there's still need for more scientific research to be able to relate to that.
Yeah, that's a general challenge. No one likes to talk about the failure of his additive manufacture parts. That's why this conference is so important.
Yeah.
So we also look into the things that are not always working perfectly. But thanks a lot for this interesting insight into a slightly different additive manufacturing process. So thanks again, and again, please look at Luca's YouTube presentation, and we hand over to the next presentation, which is going to be given by Gao Boyang from University of Science and Technology in Beijing. And the talk is entitled Effect of Scan Strategy on Gamma Titanium Aluminides based composite fabricated by selective electron beam melting. So Gao, please give us a short introduction into your research.
Okay, thank you. Could you see my screen?
Yeah, we see the screen, not in the presentation mode yet, but we can hear you and see your screen.
Okay, thank you. Hello, everyone. I'm Gao Boyang. Our study focuses on the influence of EBM parameters on the microstructure and high temperature mechanical property of titanium aluminum-based composite, as well as the layered microstructure. For the materials and methods, the titanium powders was mixed with titanium carbon by ball milling. Then the composites were fabricated by EBM process, including layer, powder, preheat, semi-melt, and melt. The layer thickness is 70 micrometers. 2 EBM samples were fabricated with a similar air energy, but sample 1 was processed using a faster scan speed combined with lower line of sight, whereas sample 2 is offsite. The result of XRD shows the parameters has no effect on phase component, and the titanium carbon was not found in the as-built sample. Instead, titanium 2 aluminum carbon phase was formed. The microstructure of sample 1 is shown at the right. The microstructure, the matrix microstructure is homogeneous duplex microstructure consisting of alpha 2 and gamma lamellar colony and gamma grains. Black contrast particles dispersed in the matrix, which can be identified as titanium 2 aluminum carbon phase by ETM. The particles exhibited 3 types of morphology: near spherical, rod-like, and cluster. The layered microstructure is observed in sample 2. That is alternating layers of dark and bright contrast. The alpha 2 lamellar seems finer in the dark layer, and the morphology and of carbides correspond to the matrix. That is, most particles show the roll-like shape in dark layer, and but the coarse near spherical particles were dominant in bright layer. Less alpha 2, more gamma, and carbides were found in the dark layer. Overall, compared with sample 1, sample 2 has more alpha 2, less gamma, and carbides. So to summarize, the use of low scan speed and large line of sight resulted in layered microstructure. For the matrix, we analyzed the elements distribution by EDS. The dark layer is rich in aluminum and poor in titanium and niobium, while the bright layer is opposite. According to the titanium phase diagram, higher aluminum content leads to more gamma phase, so the region rich in aluminum from the dark layer. We analyzed the carbide behavior by comparing the microstructure of semi-melt top layer and central of as-built sample as shown in the figure. After semi-melting, the near spherical carbide formed where the peritected reaction distributed randomly, whereas the carbides with roll-like shape precipitated from the titanium aluminum matrix. It can be seen that most carbides were melted after melt, however, increased in the as-built sample. Also, the roll-like shape carbides precipitated occurred during thermal cycles and thermal exposure, given that the solubility limit of carbide in alpha 2 phase is higher than gamma phase for titanium aluminum alloys. More roll-like carbides were precipitated from the dark layer. The strength of sample 2 was higher than sample 1 at 800 degrees centigrade, whereas similar at 900 degrees centigrade. It is attributed to the more carbide in sample 1. The tensile fracture morphology of sample 1 and 2 were similar, fractured in a brittle manner at 800 degrees centigrade. The crack initiation from a pore at 900 degrees centigrade. The fracture morphology consists of ductile and brittle fracture. The ductile fracture was characterized by dimples. It indicates that the ductile brittle transition temperature is between 800 and 900 degrees centigrade. In summary, we can draw the conclusions. First, the layered microstructure perpendicular to the build direction was formed by materials utilizing lower scan speed and larger line of sight. Second, no influence of layered microstructure on the tensile property at high temperature for the composite was found, but the gas pore may lead to the cracking. Carbide is beneficial to improve the tensile strength at high temperature by precipitation strengthening. Also, the evolution of layered microstructure and its thinness need to be further analyzed in combination with simulation. This will be carried out in our future work. Thank you for your attention.
Yeah, thanks a lot for this interesting presentation about the very challenging material. So there hasn't been too much work on these titanium aluminides in additive manufacturing. So I think this is really an interesting insight and a well done research project. Looking as we have a little bit of time for questions here, and I don't see one yet, but I have a couple of actually. So you need to process your materials at quite high temperatures, right? Some 800, 900 degrees C. So how about the reusability of the powder afterwards? I mean, that's for the raw material in powder form, quite demanding temperature already. So do you have an idea how completely you can recycle the unused powder? Is it still usable for a second build job? I think there's a Gao. Can you still hear me? think because she's frozen. Can people hear me?
Yes.
Yes. Okay, the problem is not on my
Yes.
because I think she's frozen, right? I think we've lost her.
It was too difficult question, maybe.
No, I don't think so. It's okay. Whatever. I think we can stick to the schedule. So we have lost Gao. Yeah, unfortunately, there seems to be a problem. Anyhow, some technical. So the good news is I got a hold of Martin Schwentenmein. So he will. I'm not sure if he's already in here, but he will resume his presentation after Zoltan Mayer's presentation. So if people are interested in this project on additive manufacturing of cellular ceramic structures, you can ask Martin Schwentenmein at the end of the session, so 15:20. Otherwise, we go back into our schedule to the next presentation. So the last two ordinary presentations in this schedule. The next one given by Hannes Oberlercher. He's also from FH Kärnten, and he's going to talk about additive manufacturing of continuous carbon fiber reinforced polyamide 6, the effect of process parameters on the microstructure and mechanical properties. Oberlecher.
Yes, I'm here. Yeah. Thank you, Mr. Professor Stampfer. You can hear me?
We hear you, but we don't see you yet.
Just a moment. Now?
Yeah.
Perfect. So I will try to share my screen. You can see the presentation?
Yeah.
Yeah, perfect. So, hello everyone. I will present you our results, our research results about additive manufacturing of continuous fibers. So first of all, we analyzed and worked with the Mark-forged printing system. So they work with a pre-pack filament. So in this pre-pack filament are the reinforced fibers distributed in the matrix material. And yeah, this filament is melted with the printing nozzle, and with this nozzle, the filament is printed to the composite. And yeah, we made the analysis about the microstructure, and you see here in the picture, there are a lot of cavities inside, so imperfections. And of course, this leads to a reduction of the material properties. And therefore, this technology cannot use its full potential in point of reinforced behavior or reinforced material. So why appear these cavities? So it's a point of deconsolidation or relaxation of the material. And this is a clear indicator of poor process parameter selection and inadequate in situ or consolidation. And that was important to look in our experiments. So we used a Mark-forged printer, Mark II printer. So we modified, and with a reduction of the layer height, we given a higher pressure, a consolidation pressure on the filament. And you can see the results. That is one printed single line, and probe A is with the lowest consolidation pressure, and probe D is with the highest consolidation pressure. And you see on probe D low content on cavities. And next step, we also made 3-point bending tests. And you can see there, we had their improvement of strength about 44% from probe A to D. And also in the bending modulus, about 25%. So in 0 degree of fiber direction. And 90-degree fiber direction, also improvement about 26% from probe A to D, and 43% from probe to D in the bending modulus. But with this Markforged technology or consolidation technique from Markforged, we are quite limited with the consolidation pressure, because the nozzle tip gives a little bit of grinding on the filament and too much mechanical load. So there, the fibers are breaking, and then the material lost its reinforced behavior. So therefore, we developed our own 3D printer head with a smoother consolidation unit, with a consolidation roller. And with this, we was able to give a higher consolidation pressure. And we also increased the consolidation pressure about maximum 4.2 Newton. And here are the results. So the probe C is with the highest consolidation pressure, well distributed fiber. The fibers are well distributed in the matrix, and the low content on cavities. Next, we printed a laminate, so with 2 layers, and with the printing speed for Markforged with 50 millimeters per second. We have there also a lot of cavities inside between layer 1 and layer 2. And yeah, that's a sign that there is too low heat transfer into the substrate to come up to the melting temperature. So we decreased the printing speed up to 5 millimeters per second. And you can see there a low cavity content. And yeah. So let's come to the conclusion. So with this strategy, or with the optimization of the parameters in point of consolidation and speed, we could achieve that we enhance the material properties and also reduce the cavity contents inside. In future, it is planned that we build up a kind of simulation model or consolidation model. And this consolidation model should predict the content of cavities inside, and there are necessary process parameters in point of consolidation pressure, speed, and temperature. And after that, also make experiments with this process parameters and compare this with the theoretical results. Okay, yeah, that's all. Thanks for your attention, and feel free for questions, please.
Yeah, thanks, Hannes Oberleicher, for sort of very interesting material in terms of improving strength and reliability of additive manufactured parts. Looking into the chat and into the participant list. So far, no one is raising his hand. I've noted some questions here. So this idea of consolidation is very, very appealing. I think maybe not only for fiber reinforced parts. Could you imagine that such consolidation could also improve the interlaminar strength of FFF parts, also not only for fiber reinforced parts, but also for bulk polymer parts? Would that be helpful in your view?
Of course, why not? Because especially in the in this simulation or this consolidation model, there are especially important the polymer itself, the matrix material, and if you can optimize this process, this consolidation process as whole, you can see it here in these 4 phases. You can reduce also, and just only in the polymer, the cavities content, if there are cavities inside, of course. And I see there, of course, an opportunity to use also this consolidation for this kind of materials.
Also, in this sense, it could be beneficial, but on the other hand, you probably will lose some resolution, I guess, if you just squash down the strains which you deposit on the part. So can you give us some idea about the feature resolution you can achieve in such a process?
Resolution in what point do you mean it?
Yeah, so for example, the smallest channels you can make, or how sharp can a corner be? Also, what
okay.
smallest feature size you can print?
Yeah, it's depending. So that for that this consolidation unit here, what we planned, it's yeah, it's really wide, and so it's not really good to consolidate, so edges and so on. So maybe there needs more development in the geometry and also maybe in the consolidation generally. So it should not be necessary to have this consolidation roller. So maybe there gives also other solutions in point of geometry to find also for that cases a way for consolidation.
Yeah, so meaning that's still somehow a challenge.
Yeah, of course, yeah.
Yeah.
For different applications, of course, it needs special solutions.
Okay, great. Again, we are perfectly in time still. So thanks once more for your insight into carbon fiber reinforced 3D.
You're welcome. Thank you.
And we come to the officially last and unofficially second last presentation because Martin Schwentner will be attached after Zoltan Mayer's talk. So Professor Mayer will give us a presentation on characterization of the fatigue behavior of selective laser sintered thermoplastics. He's professor for polymer processing at Johannes Kepler University in Linz and a well-known expert in additive manufacturing and also in fracture mechanics of polymers especially. So Zoltan, we are looking forward to your short presentation and the insights we gain from your presentation here. As we see you already, I see also the presentation.
Yeah. Thank you very much for the nice introduction, expert. I don't know, I think the young colleagues are much more expert in these topics than me, but we are dealing with these problems, and of course this is a cooperation in my team. This is also the part of a larger project, and we are dealing with some characterization of selective laser sintered materials. And for wider investigation, we have very simple commercial grade polyamide 12 and thermoplastic polyurethane powder. And this was then manufactured, printed in specimens. And specimens with this cylindrical geometry, does it mean what you see is a kind of dumbbell, cylindrical dumbbell specimen, and the printing orientation was perpendicular to the axis of the specimen, and then also parallel to the symmetry axis of the specimen. On the other hand, you see we have a cylindrical specimen, and in this case we have a kind of hollow geometry. Does it mean like a real cylinder? This is the specimen. And in addition to this, we use different notches. In this study, I used only the classical circular notch or notch with a larger radii in order to investigate the strengths, the monotonic tensile strength, and also the fatigue behavior, as you see. And for the fatigue behavior, we perform the test both under load and under displacement controlled loading conditions, especially for the thermoplastic elastomers. There are many publications in the literature about the fatigue behavior, whether the fracture mechanics is preferable for elastomers or the conventional Euler curve. We have larger studies, and we compared the laser sintered materials with injection molded and materials, and then in this case to the symmetry we used displacement control test, and also as classical in a fatigue analysis we use different air ratios in order to also get the influence of the mean stress. And we have done 0.1, 0.1 and -1. In addition to this, we are planning also torsional test and axial torsional test. This is one of the main advantage of this specimen, that you can perform tension compression, torsion, and axial loading and torsion in one specimen geometry. On the other side, you see then the results of the first experiments, both for the notched and hollow specimens, the monotonic test. And in this case, one of the main goals was also to derive material model parameters for elastic, hyperelastic, this is the rubber character, and viscoelastic, those are elastic plastic or elastic viscoelastic models. In order to get elastic viscoplasticity, we change also the loading rate over 4 or 5 decades for this specimen. Does it mean we have the strengths, we have fracture strain, and then we have then the deformation behavior. In the cyclic loading, according to my behavior, according to my opinion, we try to connect fatigue with viscoelasticity, and then hence with these specimens we perform also dynamic mechanical analysis. Then these dynamic mechanical analysis curves summarized in classical polymer master curves for both orientations, for 0 and 90, and then determined Pruni series for viscoelastic model. Hence, we have models for anisotropic viscoelasticity for the further simulations. Then perform the fatigue test with different amplitudes at 5 or 6 stress levels. And you see the points of the different specimens with different air ratio and with and without notch. As expected, the worst case behavior is the 90-degree specimen with a stress ratio -1, and the best case is the 0.1 with 0 printing direction. For the comparison, also so-called local strain-based Euler curve for one selected setup. And in this case, you can compare the critical strain as a critical durability strain for injection molding and for the laser sinter. Then you see there is a large difference between these two materials. Thank you.
Yeah, thanks a lot, Zoltan. We have time for questions and discussion. And I might start. In your presentation, in the YouTube presentation, you also showed the results on your cellular materials.
Yes.
And looking into one of the general challenges when we talk about elastomers, the temperature dependence of the stiffness and all mechanical properties. So looking at what you showed in your presentation there, so getting flexible materials by using a hard bulk material like polyamide, do you think this would be an option to somehow make these elastomeric structures less temperature sensitive, also using a not so temperature sensitive thermoplastic material like polyamide and making the flexibility using the right geometry?
This is an interesting question, but this is an engineering problem. Whether I have bending flexibility or bending and torsional, or I have also stretching flexibility. And for example, if you design this kind of lattice cells dominantly with a stretching behavior, with tension, then you can use this. On the other hand, if you design a bending dominated geometry, then in this case you can use the lower bending stiffness or the bending higher bending compliance. But I personally would prefer the stretching. This is I push the students to develop stretch based structures. But both options are available.
Yeah, but it's not a general solution for everything, it seems.
No. But this is might be the key. This is the interesting, whether I design a structure with bending or with stretch. And if I have a low bending stiffness, then I can use higher modulus values in a more flexible and a more compliant structure. Yeah, that is. This is, for example, an example for that. This is polyamide, and there is another one with other elastomer. Does it mean you can combine?
No. Okay, thanks. I think I don't see any further comments for the time being. I mean, we are perfectly in time still. So officially, the session is already over now. But if people want to listen quickly to Martin Schwentenwein, I invite you. So again, please look also at the YouTube videos. There's lots of interesting information in addition to what we hear in the short presentations. And Martin, you can just give us a 1 minute insight into, or 2 minutes, and maybe people have some specific questions for your research on ceramic cellular structures.
Yeah, thanks Jürgen for the introduction, and then sorry for the inconveniences for those who were waiting for my talk during the originally time slot. That's one of the perks of these virtual meetings, but I'll promise to keep it short and not take away too much of your well-deserved break time. So the subject of this work was lithographic 3D printing of tricalcium phosphate ceramics. And this particular class of ceramics is a very interesting material for medical applications, in particular for the field of tissue engineering, because the ceramic resembles the inorganic content of native bone tissue to a very high degree. So if you implant that, the human body is capable of resorbing that material and remodeling it into actual bone tissue, making it a very interesting substance if you want to replace damaged bone after traumatic injury or tumor resection or other things. And the very interesting thing about 3D printing here is that you can provide a very complex and defined geometry, especially when it comes to porosity and interconnectivity of pores. So I'm not going to explain 3D printing in front of this crowd. I just would like to stress here that with this lithographic printing approach, we are not ending up with the actual ceramic directly after the printing process, but it's a two-stage process. We're first printing a so-called green part via lithography, so a photopolymer that keeps the ceramic particles in place, and then a subsequent step, we are getting rid of this polymer carrier and end up with the pure ceramic material. And the idea of this work now was to try out different lattice geometries, different porosities, and to check their effect on the mechanical properties. And what we found out is that on the one hand, it was possible to get to very nice resolution, very good precision, some slight deviation. So channels tended to be slightly smaller than in the underlying CAD model, which is a well known and understood phenomenon for particle field suspensions in lithography based printing. So there are certainly ways to overcome these challenges. But the more interesting findings were that with compression tests, we were able to show that with defining and tailoring the porosity and the lattice geometry, we were able to adjust the strength of the final sintered ceramic. And by doing so, it was really possible to get close to the actual mechanical properties of native bone tissue as shown in this particular figure. And if you want to, of course, hear more about that, please check out the YouTube video. But for now, I'll keep it at that. If you want to also dig a bit into the biology of these things, here you can find an open access paper where everything that was highlighted in this brief presentation is also explained in more detail. And with that, I would like to keep it. And if there are any questions, I'm happy to answer them.
Yeah, thanks, Martin. So we have now finally seen everything from ceramics, metals, polymers, composites, and as expected, fracture mechanics play an important role everywhere, and should encourage us to not forget about fracture mechanics, what people usually like to do. So do we have some comments and questions to Martin from the audience? Seems no urgent things to clarify. So I want to thank all the speakers once more. So I really liked what I saw, to be honest, and also encourage people to look into YouTube for other things you are more interested in. There's lots of information in the YouTube presentations. But for the time being, I want to thank our speakers and also the audience for being here. And after a short coffee break, the conference will resume according to schedule. So thanks to everyone. See you later.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Goodbye.
in Coimbra University. So the purpose of the present work was to study the fatigue crack propagation under biaxial mode, mode 1 and mode 2 loading of the titanium alloy TEIL6V4 parts manufactured by laser powder bed fusion. The main objectives was the effect analysis of two main parameters, the loading angle and the effectiveness of the literature mixed mode crack propagation models for, in this case, for laser powder bed fusion. So we used the geometry presented in the left is the compact tension shear specimens, and the figure of the right presents the loading device developed accordingly to Richard for this kind of specimens. In this kind of device, where the loading angle alpha is defined, we can perform different tests, crack growth tests, with different loading angles, and we measure the crack by an optical device, and also we measure the crack, the loading displacement, the displacement of the crack with a Dick system that can be seen in the back of the photo. So, sorry, the loading angles in the three cases, we analyzed three loading angles, 15, 30, and 45. And in the three cases, the angle of the crack was more or less similar, around the 20 degrees. This means, and also the crack closure perimeter was also similar. This is the load ratio perimeter, U against delta K equivalent, and is similar for all the, was observed to be similar to all the loading angles, a little bit more lower the crack closure level for the three loading angles than for 0 degrees, but similar. So that led us to these results. The crack growth rates were determined, used several methods of the literature, and the speed didn't suffer significant alterations for the loading angles analyzed, due similar values of the crack deflection, and also by the similar loading, the similar values of the crack closure level. And with that, I conclude this brief summary. I'm open for questions.
Thank you very much. That was very interesting. I'll open the floor to some questions, please. Okay, I have a question, if I may.
Yes, of course.
I'm very interested in the use of DIC and Arcan mixed mode type testing. I'm curious to know if you also considered some form of field fitting to extract the mixed mode fracture parameters or energy integrals around the crack tip.
Oh, that's a nice question. We did one of the methods that we used was made by finite element analysis, not using the Dick system. We determined, we analyzed more than 1,000 cases of position of the crack, and then we calculated the J integral, and with that we can calculate the crack parameters, the delta K parameters.
Okay.
But not with the Dick system. That will be very interesting in the future to do that. Very interesting.
Okay. Thank you. Are there any other questions from the floor? Okay, well, since we still have some time, I have another question, if I may. You reported that you didn't really observe significant difference in closure effects. So previous work that we've done on laser powder bed fusion TI-64, we noticed significant closure behavior at near threshold fatigue crack growth rates. I'm not sure if you've gone that low, but I was just curious if you've observed, or did you measure at near threshold fatigue crack growth rates?
No, Torsten. Indeed, the analysis that I have presented is only for the Paris regime.
Okay.
This is the first analysis in laser in SLM materials, but I have done the same analysis in aluminum alloys, in the 6C82 aluminum alloys. In that case, you are right. In near threshold, the shear parameter, the shear K is very important, and generally crack closures increases a lot.
Okay, thank you very much. Okay, are there any further questions from the floor with regards to the talk? Well, I'll want to thank you again for a very interesting talk. I presume the audience can contact you if they have any other questions they would like to ask. And with that, we're slightly ahead of time, but I think it's okay. If you don't mind, we can move to the next speaker. You can please share your screen. Thank you. We can see your screen. So when you're ready, please go ahead. Currently can't hear you, so I think you're still muted. I think you're still muted. Are you still there? Okay, I'm just going to give it a few minutes to see if the speaker will join us again, hopefully.
Yeah, sorry about the delay because there was some problem with the Zoom.
No problem. We can hear you loud and clear. So when you're ready, please go ahead.
Yeah, I can start with a short summary.
Thank you very much.
Yeah, so today I will talk about the formation of bilamellar microstructure in LPBF process Ti64 and its effect on the quasi-static and dynamic mechanical behavior. So one of the major challenges of LPBF of Ti64 alloy is the extremely high cooling rates that are involved during this processing results in the formation of martensitic microstructure, and which is extremely brittle, so we cannot use that in real engineering applications. And in the applications such as automobile or aerospace industry, we need high fatigue performance, like we need to delay the damage initiation and slow the crack propagation. So hence we need a post-heat treatment of the as-built part. So in literature, there are different microstructures which have been generated for Ti64, such as lamellar, equiax, and bimodal. And for the conventionally processed Ti64, the lamellar microstructure has highest resistance against fatigue crack propagation, but this microstructure suffers from poor mechanical properties. So now the objective is to design a heat treatment by which we can generate a microstructure which has good resistance against crack propagation, but at the same time it should have better quasi-static properties. So for this, we developed a two-step heat treatment. So first step involves heating it up to above beta transfers, so that's a single phase field, and then cooling it slowly. So we transform the as-built martensitic microstructure into a lamellar one. The second step, it involves the aging of the lamellar microstructure in the temperature range of 800 to 960, followed by air cooling. So the second step, it transforms the lamellar microstructure into a bilamellar. So bilamellar is a duplex microstructure in which one phase is a primary alpha, which is seen as a dark phase on the micrographs on the right-hand side. And the white phase is a beta, but in this beta, there are nanoscale precipitates of alpha, which are formed during the air cooling of second step. And with the temperature of the secondary heat treatment, we can play with the phase fractions of primary alpha and the transform beta phase. Then we did the uniaxial tensile test, and then we saw that for the microstructures that were obtained at 880 degrees centigrade, we saw increase in the yield strength compared to a lamellar microstructure, whereas for 960 bilamellar, we saw a decrease in strength, and we can attribute it to the strength of these microstructure to the deformation mechanism. So for the microstructure which was obtained at 800 and 880, there the dislocations from primary alpha, they cannot cross into the transform beta phase. Hence, they get blocked at the interface, and when there is enough dislocations are getting blocked due to stress concentration, voids can be formed. And the microstructures on the right, they show so these microstructures were taken from the failed tensile bar. So for the sample that was heat treated at 800 and 880, we can see that the voids are forming at the interface of these two phases. Whereas for the microstructure that was heat treated at 960, the dislocations can easily cut through the transform beta phase also, and hence we see voids are forming in a straight line along the slip lines. Hence, we see that for certain temperatures, we have the increase of yield strength as compared to the lamellar microstructure. Now, coming to the dynamic behavior, so we did fatigue crack growth tests for the Paris regime. So it was in tension mode, and the load ratio was 0.1. And here, if we look at the Paris law equations for different microstructure, first thing that we see that the exponent of delta K, it shows how fast the crack is propagating. So I took the value for the as-built microstructure from the literature, and it was around 4.76. And if we compare these values for lamellar and bilamellar microstructure, we see the values are significantly smaller than the as-built one. Thus, it says that the crack propagates slower in the heat-treated microstructure as compared to the as-built. But if we compare lamellar and bilamellar microstructure, there is not significant difference. We can consider them as a similar behavior. So now if we take a look at the microstructure after the crack growth experiment, we see that in both of these microstructure, we see ups and downs in the crack profile. That means the crack was deflecting when it was traveling in a straight line. Also, we see that there is a presence of secondary crack in both of these microstructure. Thus, these two microstructure behave similarly in terms of crack propagation. Hence, with the two-stage heat treatment, we can improve the quasi-static mechanical strength, whereas at the same time, we have maintained similar crack propagation behavior. So this was the conclusion of my study. If you have any questions, I will be happy to answer them. Thanks.
Thank you very much for an interesting talk. So I would like again to open any questions to the floor, please. Okay, if I may, I have a few questions that I would like to ask. So part of your duplex heat treatment, you chose to go in the first cycle above the beta transist temperature. What was the reason for that?
This was to ensure that, because I wanted to make a lamellar morphology. So I knew that if I want the lamellar morphology, I need to heat it up above beta transist and to cool it down. So that temperature was taken as a kind of an arbitrary, because I knew the beta transist was around 1005 degree. And so if I go 30 degree above, then I'm completely ensured that everything is beta. So that's how I chose the temperature. Okay, and did you at all measure the prior beta grain structure before and after your heat treatment? No, that is still a part of an ongoing investigation that we are trying to see how the grain size changes when I do this heat treatment. But for the moment, I have not looked at it. Okay. I mean, if I'm just sharing my thoughts here, if I may, I'm concerned about prior beta grain growth, which would be the result of going above the beta transist temperature. Yeah, that is true. And that would
degrade elongation to failure, so ductility. So that's why my second question is, you reported the tensile strengths. What was your elongation to failure or your ductility for the tensile?
For the bilamellar microstructure, I had similar ductility. It was around 10 to 12% in between that. And for lamellar, I had slightly higher because I think the strength was lower. So that is my, yeah, so those were the results. That lamellar had slightly higher ductility, but the bilamellar, they behave similar way.
Okay. Again, any questions from the floor with regards to this work? Okay, well, then I would like to thank you for your talk, and I hope you all go and if you haven't done so, watch the video presentation. So thank you very much.
Thanks.
Okay, so we're very much on track. We're still slightly ahead of schedule. So if you don't mind, then I suggest we go to our next speaker to listen to the next talk. Thanks. We see you. We cannot yet hear you. I think you are still muted.
No? Hi?
Hi, yes.
Can you hear me? Yes.
Yes.
Hi. Just to say that I'm here with my PhD student, Pedro Costa. He's going to present our work, okay?
Okay, perfect. Thank you very much. So when you're ready, please go ahead.
Okay, thank you.
Thanks.
Greetings.
Hello. So when you're ready, please go ahead and share your slides and yeah, go ahead. Thanks.
Okay, just a second. So can you see the PowerPoint presentation?
Yes, we can. Thank
okay,
you.
perfect.
We can hear you, so you're all set. Thank you.
Okay, thank you. So greetings, everyone. So we will be presenting a gist of our study on influence of finishing in titanium Ti6Al4V AM specimens under very high cycle fatigue conditions. So we tested titanium Ti6Al4V manufactured by the selective laser mapping method. All specimens that we manufactured were made in one single section vertically, including ultrasonic specimens and the mechanical basic properties determination specimens. No heat or hot isothermal pressing treatments of any kind were conducted to all manufactured specimens. And these are the properties here presented that we first determined, and the microstructure of alpha-alpha coma titanium face plates. So the applied technology is the ultrasonic fatigue testing machines. We use these machines to test very high cycle fatigue, which comes between 10 to the power of 6, 10 to the power of 9 cycles. This machine turns this so high number of cycles in a time reliable manner to achieve such high number of cycles. We induce resonance to a certain setup of booster, horn, and specimen in a certain resonance shape to test such high number of cycles. So just in comparison, we can achieve 10 to the power 9 cycles in less than 1 week. In a conventional machine, we can easily take more than 1 month. So because we are testing the surface roughness influence, we polished half of the manufactured specimens to a mirror-like shaped surface, and we quantified the removed layer by an optical light scanner before and after polishing treatment. We also quantified the surface roughness by interferometer, and only after all these analyses, we then conducted the fatigue tests. So just skipping just to the fatigue stress life results, we can clearly see an increase of fatigue strength when we polish the specimens. Unpolished specimens always presented surface crack initiation. Just one specific specimen presented a subsurface crack initiation, while the polished always presented a subsurface crack initiation in defects presented inside the specimen, as in regas pores, for example. So looking at surface, fracture surface, first in as built on the left, we can clearly see a surface crack initiation, even sometimes in multiple locations. When compare it to a polished surface, we can see the defect, subsurface defect that initiated crack with certain characteristics associated with very high cycle fatigue. Another important conclusion we take from our surface crack of our specimens is the fracture surface shape. When comparing it with previously published results in the same material tested in the same setup of ultrasonic machines, we can see a clear difference in the fracture surface, a more surface crack in propagation in the specimen. We attributed this effect to residual stresses present, since we did not conduct any heat treatment or any treatment to the specimens after the SLM manufacturing process. So in conclusion, yes, we conclude that surface roughness from SLM has an influence on fatigue strength. When we polished, we do have an increase of the fatigue strength of the specimens, and a different crack initiation location, being mainly subsurface when we polish the specimens. The defect size and its location also showed an important role on the effect of fatigue life and crack initiation. When comparing it to different researchers on the same material, we do have a slight lower fatigue strength, since we did not apply any heat treatment, no internal crack initiation, and a different fatigue fractures surface shape that we have associated with residual stresses present in the specimens when manufactured by SLM. So that is the gist of our work. Thanks so much.
Thank you very much for the excellent talk. Okay, so again, open the floor to questions. Seems like it's in the afternoon, nobody's having any questions. So I will take the liberty of going ahead again with a few questions that I have myself. Yes. So I found your result very interesting in terms of how the residual stress drives the crack front. I know you didn't perform any heat treatment, but is this some future work to confirm this hypothesis, to do, so, for example, a stress relief?
Yes, we actually did not expect in the beginning to see such a different shape. So it's actually a future work that we not expect to have, but yeah, it would be very interesting to play the same machine, to manufacture the same specimens, but then apply and trying to take out the residual stresses that we believe are present, and then compare the fracture shape and the fatigue strength as well. Without a doubt, that would be a very interesting future and continuous work in this subject.
Great, thank you. Jan, you have a question.
Yeah, just a curiosity question. That we heard a lot of talks about very high cycle fatigue conditions. Can you comment on the main difference in the failure of, like, for example, internal defects versus surface with very high cycle fatigue and yeah, regular fatigue problems?
Okay, so yeah, I'll make a small comment because the topic is very big. So I don't want to spend a lot of time, but when you surpass from high cycle fatigue to very cycle fatigue, there's a few changes in crack propagation and crack initiation. These are associated mainly to high hardness steels and titanium and aluminum. Not all steels have shown very high cycle fatigue, but crack initiation tends to initiate at defects where we can see first what we have called the fine granule area. We can see, for example, here on the right, a small, a more I can actually zoom it. Perfect. This area associated with very high cycle fatigue. This is one easy way to identify this sort of method, this of crack propagation and initiation on very high cycle fatigue. But beyond that point, we can easily talk a lot about very high cycle fatigue.
I think that is pretty clear, but what is like with respect to additive manufacturing? What do you see as a main difference here? Is it kind of even more surface related, or where does it start basically? It seems to start very much on the surface, as we have seen from other talks also. That,
okay, well, that will depend on the material, of course, and also in relation to this study on the fatigue, on the surface preparation. Since in very high cycle fatigue, you are very dependent on small crack stress concentration points, sometimes present in defects or on the surface. If the surface is polished, you may not have the crack initiation at the surface and initiating at defect, and thus presenting this fine granular area that we can see here. And we have other images, but in this small gist of presentation, we kind of just showed one. I'm not sure if I answered.
No, that's insightful. Thank you.
Okay, perfect.
Thank you. There's another question. Harry, if you please go ahead.
Thank you. My question is, these specimens were built with process optimized conditions. Have you made any study about process optimization before you build these specimens?
You mentioned the selective laser melting, correct?
Yes, and the optimization regarding to the total density of the specimens.
Okay, so we made these specimens through a specific company, and they do not wanted to publish the optimization parameters of because they didn't want to publish to protect their optimized process. So we cannot talk about that regard, but they do follow one optimized combination of parameters that they follow in their company. I cannot discuss that topic, unfortunately.
Okay. Have you identified any of these defects? What kind is?
So mostly the most present defects are inner gas pores on the specimens and all other surfaces that we analyzed. And since it was a very predominantly type of defect, we did quantify the size of it. I have not here on this small version of the presentation. And we also have seen very few small faucets and lack of fusions, but there were very few number in comparison to the inner gas pores.
Okay, thank you.
Thank you very much. Okay, well, I think it's time to move on to the next talk. So thanks for the questions and the discussion.
No problem. Thank you.
Okay, thank you very much. So if we can move on to the next speaker, please. If you can share your screen and your camera, if you have one.
Can you see my presentation?
Yes, I can. So when you're ready, we can hear you, we can see your slides. When you're ready, please go ahead.
I have prepared a slide with a summary of my presentation. If there's no problem.
No, of course, that's completely fine.
Okay. In our work, as the title suggests, a modeling framework for fatigue life estimation of selective laser melting additive manufacturing Ti64 was developed, and the results of the current modeling framework were compared with the experimental results from the open literature for validation purposes. The main assumption of the current modeling framework is that fatigue failure is governed by the crack initiated from only one defect, which is characterized as the critical defect of the part. The modeling framework consists of two sections. In the first section, a thermal history simulation of the fabricated part was performed in a thermal history module of ANSYS Additive Suite. And the main output of this simulation are the temperature fields and the melt pool characteristics of the part in a layer by layer manner. By the processing of these results, the susceptible areas for defect formation were determined, and the main indicator for a defect formation were the melt pool dimensions. If they do not fulfill certain criteria, the main types of defects found in SLM will be formed. Finally, from the susceptible areas, the location of the critical defect is determined, and in the present case, it is located in the layer of the thinnest cross section of the part, where the maximum stresses will be developed during the uniaxial loading of the fatigue specimen. In the second section, depending on the location of the defect on the cross section, an appropriate stress intensity factor were chosen in AFGROW software tool, and a fracture-based prediction was performed to estimate the fatigue life of the part. It should be mentioned that small fatigue crack growth properties were considered to account for the lower threshold values of SLM Ti64 due to the negligible effect of crack closure. And as it can be seen, a good correlation with experimental results was achieved, as the predicted results lie in dispersion of the experimental ones. And I finished my brief summary of, I tried to be quick.
Good, well, thanks, that was a good summary. Can I open the floor, can I ask the floor for questions? Okay, well, maybe I can get some discussion started. So in the previous talk, we heard that they observed multiple initiation sites, and your model assumes that it's only one critical defect. What's your justification for that, and how would your model differ, or how would you incorporate multiple defects initiating?
The main reason that we assume that the crack initiated from only one defect is by the literature review of experimental results. In the most of occasions, there is the crack initiated from only one defect, and in the current experimental in the experimental study on which used as a reference, only one defect was the main crack. From only one defect, the crack propagate until the final failure of the specimen. And I think that is the general trend of the literature results regarding the experimental failures, the observation of experimental failure. That's why we use this assumption.
Okay, I mean, I would argue that it probably depends on, well, the defect population size, so the spread in size. So you could have a critical defect that is similar in size to the general defect population, and then you probably will have multiple initiation sites. And I also think it might depend on the surface finish. So for a machined and polished sample, again, I could see that
in the present study, the reference case, in the reference case, the experimental specimen was polished. So there is no any surface roughness effect on fatigue properties.
Okay. Okay, and then I'm just curious, one of the big factors in using, for example, FGROW or fracture mechanics-based crack growth data is the geometry functions. And so I wanted to ask, what geometry functions did you use for the assumed initial defect?
The present case solution accounts for the surface, the crack initiated from a surface of a road, from a cross section of a road.
Okay, but if you said the sample's polished and the fatigue cracks don't initiate from the surface, how does that?
Can you repeat, please?
Previously, you said that you didn't, your samples were polished, and so there's no initiation from the surface. So I'm trying to understand how the two fit together between the model of the surface crack.
Our thermal history prediction, by the processing of the outputs of our thermal history prediction, the melt pool on the surface seems to be insufficient overlapped with each other. So lack of fusion defects were formed in the surface of the cross-section.
Okay.
So this is the defects from crack, from which crack were initiated, was initiated.
Okay, thank you. Jan, I see you have a question. If you please go ahead.
Maybe I just didn't get it, but how do you determine the critical defect? What is the underlying assumption of what does the defect have to be critical? Because I'm guessing that's detrimental or that's decisive of this kind of approach.
By processing the results of thermal history, we get the melt pool characteristics of the part. We found on our work that the melt pools in the surface of the part did not fulfill the criterion for lack of fusion. They present a insufficient overlap. From these melt pools, from these areas of defects, the most critical one is the area on which the maximum stresses will be developed during the experimental testing. It's a fatigue specimen that a uniaxial loading is applied on it. So the thinnest cross-section, on the thinnest cross-section, the maximum stress will be developed. So the thinnest cross-section so the defects on the thinnest cross-section were considered as the critical.
Mm-hmm.
I hope I answered your answer.
Yeah, I'm just wondering how that would look like in a real component. Would you then? You would only look at the highest stressed sections, right? Independent of the notch.
This is a issue under investigation. This is a first study, so we can move later to the study of a realistic part, where it's not sure that the crack will initiate from the location of the maximum stresses.
Okay.
This is just a preliminary study to go to a more realistic one.
Okay, thank you.
Thank you very much. Bo, a quick question quickly, and then I'll have to move on to the next speaker.
Yeah, I have a quick question about how you define this critical defect. Have you considered their shape, or because of the sum of the defect gonna be linked to the microstructure as well? It depends on their surrounding areas. So I understand it's you can say it's from one defect, but how you quantify the critical defect? Thank you.
Regarding the shape, only the shape.
Sorry, so you only consider the shape. So you basically consider the projection area of the defect. That's it. Not consider the aspect ratio.
Of course, we do consider the aspect ratio. It's not in my presentation. In my amazing presentation, it is referred how we model the defect. The defect was considered as a semi-elliptical crack on which the aspect ratio was considered. And regarding the size of defects, we were based on the experimental observations of the fracture surface of the specimen.
Okay, thank you.
Okay, thank you very much. I'm going to leave it here. So thank you for your talk and the lively discussion. So let's move on to the next speaker, focusing on 17.4 pH steel.
So, hello, can you hear me well?
Yes, I can hear you.
Yeah, actually, I am Giannella. I am the second author of this research. If I'm allowed, I will be the presenter instead of Professor Sepe. Will that be possible as well?
Of course, please go ahead.
I've prepared just a couple of slides through which I will make for you a brief summary of our research. Let me share the screen, just a second.
Okay, we can see your screen and we can hear you, so please go ahead.
Okay, thank you. So we are seeing, assistance during this conference, that there are several research efforts aimed at increasing the sizes of the components that can be produced through additive manufacturing techniques. So we try to do that in our research. We simply try to do that through the laser beam welding process. So we tried to understand if the welding process can degrade and how much it degrades the mechanical performances of the final components. So we made this quantification through tests at the level of uniaxial specimens. This is so the basic idea is that we could use the nowadays existing joining technologies to join additively manufactured parts so as to increase the size of the products. First of all, we manufactured a lot of plates through a laser powder bed fusion machine, and then we joined these plates through the laser beam welding through a welding head moved by an industrial robot. Then we optimized the welding parameters so as to guarantee the lowest possible amount of imperfections. So pores, voids, whatever could affect our weldments. In final, we, looking at the top right corner of this slide here, based on the optimized parameters, we welded 4 plates and we cut specimens from these plates so as to carry out mechanical tests for these specimens. We made static and fatigue specimens, and we carried out static and fatigue tests on these specimens in our laboratory. So at the top left corner, we can see a picture of the welding cross-section where we can see that the weldment was fine with no big defects. At the bottom left corner of the slide, we can see a picture of a fatigue test specimen with a close-up showing the very narrow welding line. This welding line was produced by the laser beam. At top right corner of this slide, we can see inside the results in terms of quasi-static stress strain curves, where we compare the results of these welded specimens with those of the as-built specimens, then without any weldment. We can see that the failures occurred sufficiently far from the welding line, and looking also at the fracture surfaces, we observed similar structure in red between the welded and the as-built specimens that we can see in the black square. So also in terms of mechanical properties we obtained from these tests, we did not notice any difference, any appreciable difference between the specimens at the level of significance of ±2 sigma, so 95%. At the bottom right corner of the slide, instead, we can see the Welder diagram we derived from the fatigue tests. We obtained an endurance limit of nearly 270 megapascal, that is nearly equal to 55% of the yield strength of this material. Now, we are currently performing further fatigue tests on both the welded and the as-built specimens, then without any weldment, for a comparison. And that is all. Thank you for your time. Please, if you have any question, I'll try to answer to the best of my knowledge.
Thank you very much. Yeah, so are there any questions? I'll opening it up to the floor. Please, Benjamin, go ahead.
Yes, hi, thank you for this great presentation and another investigation on welding of AM materials. I have two questions concerning the fatigue test results. The first one is about the evaluation. Which evaluation method did you use, and how did you define the knee point and the slope after the knee point? Since when I'll take a look through the results, I could also imagine that there is no knee point depending on how the test results might come out at lower load levels concerning or towards the long life fatigue regime. So this would be the first one. Yeah, and maybe the second one is about, yeah, you can answer it at once. Is about mean stress sensitivity, since this is tested at R-1, and you said that there are ongoing testing. Is it also planned under pulsating loading, so that fatigue test results could be compared with the recommendations or with other investigations on conventionally joints, for example, which are usually under pulsating loading or R0.5, for example?
So thank you for your question. First of all,
yes.
It's quite long.
Yeah, sorry.
Yeah, doesn't matter. So these are just preliminary results. These are based on tests on at R-1, so 0 mean stress.
Yeah.
We are currently performing further tests at lower load levels, so as to point out perfectly the knee point of the Welder diagram or the Welder curve. So we are performing now tests at low level at 250 megapascal, something like that, and we realized that actually the knee point is precisely 270 megapascal, more is roughly speaking 270 megapascal. So we are seeing that some specimens run out and some specimens fail at a couple of millions of cycles. We do not intend to perform tests at pulsating loads. So the first step ahead of this investigation is to compare these results with the results that we want to obtain from as-built specimens, so as to understand if the weldment can cause the failures or is the material itself that causes the failure. So the first comparison is as-built and welded specimen. And then we can perhaps think about different pulsating load or whatever else.
Okay. Yeah.
Have I answered the question?
Yeah.
Okay, thanks. If I may, I have a quick question. So one of my understanding of the concerns when producing 17.4 pH steel in AM is the formation of precipitates, composite precipitates. Did you do any detailed microstructure analysis across the world to observe
Yes, we did that in a previous research where we actually investigated more on the welding of the plates. We did also some further microstructure evaluations, but I'm not actually the expert of this field, so I just need to ask to my colleagues to answer this question, because I'm not an expert of microstructure or whatever that they did in the past.
Okay.
Sorry about that.
No problem. I'll leave my question. Are there any other questions in the floor? Okay, then thank you very much for your interesting talk, and we will move on to the next presentation.
Let me stop the sharing.
So just briefly, before the next speaker starts, I've been informed that Professor Bochen will also present his talk afterwards, after the last talk. I believe he's been moved from a previous slot to present after 1640. So please don't leave after this talk. Okay, well, when you're ready, please, we hear you. Your screen.
This
Can you see the screen?
Yes, we can see the screen, and I can hear you loud and clear.
Thanks.
Please go ahead.
Yeah, cheers. So good afternoon, I'm Nick Barnard. I'm a research officer at Swansea University. This is just a quick summary of the work we've been doing at Swansea with our industrial partners at Rolls-Royce. We've been looking at the use of blown powder titanium alloy type 6242 for the use in aero engines. And we've been mainly involved with the mechanical testing of this additive material. What was included in the presentation was the initial results of a series of high cycle fatigue experiments on this material. The motivation for the work was pretty simple: to determine the suitability of the use of this technology in the repair of expensive parts that have been damaged in service. Previous work had been done on blown powder Ti 6242 alloy on a wrought variant of itself, where the presence of the additive material appeared to be superior from a fatigue standpoint. So in this part of the project, we're trying to exploit the benefits of the blown powder Ti 6242 material onto metal alloys with relatively similar mechanical properties that are inherently a little bit less weldable than the near alpha alloy used in the blown powder. In this case, we're looking at the conventional form of Ti 6246, where the notable deviation in chemistry is in the molybdenum content. The strategy used to characterize the material was pretty simplistic in nature, but one we think captures the application quite well. We carried out a series of high cycle fatigue tests on 3 different configurations of the additive alloy. One that's all additive, Ti 6242, and 2 types of composite specimens, whereby the testing the material both in the build direction and transverse to the build direction of the material. We carried out high cycle fatigue testing at 3 temperatures, including ambient, 350 and 480 degrees Celsius. And all specimens that were tested were heat treated, machined and polished, so we weren't testing in the as-built condition. An example of the data set is given here for the 350 degrees Celsius, where the composite specimens show a small debit in fatigue life from the conventional Ti 6246 alloy in both of the orientations tested. The decrease in fatigue performance for the blown powder is modest and acceptable, although with larger associated scatter in the transverse orientation. We looked at all the fatigue failures using standard microscopy techniques and found predominantly, although not exclusively, that the fatigue failures in the material components was facets in the wrought Ti 6246 and microscale pores where failures occurred in the additive material variant. When we attempted to classify the initiating defect size to the failure cycles, we found a much greater correlation in the additive material where the pores dominated than in the wrought alloy. We also determined that the powder quality had a significant effect on the high cycle fatigue performance in the additive material, which you would expect, but highlights the dependence on the powder supply that you have. In terms of using the additive material as a surrogate or on its own, it was interesting that at ambient and moderate temperatures, the composite specimens slightly outperform the solely additive specimens, whereas at the extreme temperature, the presence of the wrought material in the composites shows a reduction in the HCF performance. The relative behavior between the composite specimens compared to the conventional Ti 6246 is consistent across all the temperatures that we tested at. The nature of the interface has recently become quite interesting to us, given we observed that a lot of the failures occurred at or close to this interface. We're currently trying to characterize that through hardness measurements, and where we've
where we have done hardness measurements, we're seeing soft areas around the interface with the presence of some necklacing in the microstructure. So in terms of the overall conclusion, we think the use of blown powder variant of Ti 6242 shows particular promise from a fatigue point of view, even when used with conventionally forged alloy. I'd like to thank you for your time and acknowledge my partners for the funding and support they've offered. Thanks.
Thank you very much. Very interesting. Yeah, any questions from the floor? Okay, if I may, I have a quick question. So I know you mentioned that the failure seemed to have occurred near the bond between the AM and the wrought material.
Yeah.
I didn't quite understand. Was it mostly on the AM side? Was it mostly on the wrought side?
It was mostly on the wrought side when you got induced the failure from at that location. There were failures throughout the gauge section, but when it did occur there, it failed from the wrought alloy.
But still close to the bond line.
Yes, yes.
Okay, and then the other interesting point I thought was the sort of, would you say there's a type of chain, or how would I say, competing failure mechanisms between facets that form in the wrought material or cause the crack to initiate versus the pores? And
yes, yeah. In the obviously Ti 6246 is particularly prone to large grains, and particularly where we've observed it, there's a chemical difference with its surrounding concerning the molybdenum distribution. But yes, I think it does compete, especially obviously these are wrought forged materials, which have, for the composite specimen, have been cut away, deposited, but then the wrought variant itself has then undergone a heat treatment designed for the additive material, which ordinarily wouldn't have been. But I think definitely competes in terms of the stiffness mismatch isn't stark, but I think that might play a part as well.
And did you observe significant grain growth in the wrought material near the bond line?
I'm trying to get more information closer to the bond line from Microstructure. Obviously, they're all broken, but we're looking into that. You don't see a clear. There's definitely a heat affected zone there, and the microstructure is heavily influenced based on that.
Okay.
But that is currently what we're looking at, both through standard microscopy and nano indentation, SPM, those sort of things.
Great. Are there any further questions? Okay, well then, thank you very much for a very interesting talk. And then we move on to our last speaker, Professor Bo Chen. So if you could please share your screen. We see you.
Yeah.
And we see your slides, and we hear you as well. So when you're ready, please go ahead.
Yes, thank you. Yes, thank you for giving me this time. Yeah, because I basically missed yesterday's my talk allocated time slot. Okay, so the technique I'm going to present quickly today is called a selective electron beam melting. So this is the additive manufacturing. It belongs to the powder bed fusion additive manufacturing, but you can operate your electron beam at the high temperature due to the so-called preheat. So in this work, it's kind of the follow-on research from my last year's presentation. So last year, we try to do this selective electron beam melted nickel-based super alloys. However, what we found out is even you fabricate these nickel-based super alloys at a high temperature, you still see a massive amount of the cracking. along the grain boundaries. And we also learned is for this type of the nickel-based super alloys, they tend to contain a high aluminum and titanium. So these fall into the unweldable group, okay? However, we can use the heap and trying to close such a cracks. And then after the heap, because of the, you will do a slow cooling, so you lose all of this cuboidal shape of the gamma prime precipitated strengthened phase. So you have to give another solution treating and aging and trying to restore the cuboidal shaped gamma prime. However, after that, you will see a massive amount of the crack reappeared in this microstructure. And then we also understood recently is for such a crack to occur, it's basically due to the solution treating. When you give the sample the solution treating, and then you suddenly open up the crack. So what we learned from this failure lesson there is that you cannot rely on the post-processing, such as the hot isostatic pressing to close these cracks. So, and then this triggers the current work. We modified the processing parameters, and by using the very high land energy input. However, when you give the high energy input, you will tend to have an uneven top surface on your powder bed. In this case, they will increase the probability to get the Lithographic defect. Okay, so we then used a new scan strategy by combining this land order with the appropriate land energy. We then get this crack-free microstructure in the sample. Okay. After we get these high gamma prime nickel-based super alloys with the crack-free microstructures, and then we tested along the build and also perpendicular to the build of these materials at both the room temperature and the high temperature up to 1000 degrees C. So they give me a good mechanical properties when compared with the cast version. However, our future work is trying to focus on the microstructure degradation, because for this high temperature powder bed, when we build these high gamma prime nickel-based super alloys, when we finish the building, and when you look at from the bottom to the top in terms of the microstructure, you can also see this TCP phase. So TCP phase has been known as one of the detrimental phase for the high temperature creep properties of the nickel-based super alloys. This is motivate us to apply the alloy design and trying to optimize the chemical composition of these nickel-based super alloys tailored for additive manufacturing. Yeah, thank you very much.
Thank you for an interesting talk. Are there any questions from the floor? Okay, well, I have a quick question, if I may. I'm not an expert when it comes to nickel super alloys, but my understanding is that the formation of the gamma prime and the precipitates and the control of that with post heat treatment is always critical. And I know you mentioned that the heat treatment was when the cracks formed. I just wanted to know, is that because of the formation of precipitates and the columnar structure that forms during the SLM process?
Okay, yeah, it's a very good question. So, so basically, we try to understand is what caused this crack formation during the heat treatment. And so far, based on the metallography observation, what we found out here is could be due to the reprecipitation during the cooling. So there is a term in the nickel-based superalloys, people call this cooling-induced precipitate, because for the high gamma prime fraction nickel-based superalloys, they tend to contain a high content of the aluminum as well as the titanium. So in that case, they have a very high susceptibility to get the gamma prime out. So even you do the normal quenching, you can still get this gamma prime out. And this kind of the gamma prime, depending on the composition range, and they could cause this tensile residual stress. So this is what we thought is when you give this heat treatment, and you generate this tensile stress because of your precise parameters haven't got to the stage to generate a very good metallurgical bonding. So with such a cooling stress, and you could just open up this crack in the materials. Yeah.
Okay, and then you spoke about in your strategy or optimizing of strategy, you spoke about the columnar or microstructure that forms. Sorry, maybe I missed this, but did you observe notable differences between a low energy input versus a high energy input and how this columnar structure forms?
Yes. So when we use the very high energy, what we tend to get is the very fine columnar structured materials. And we also did some parametric study. So when your energy is very low, again, you tend to have these very refined columnar grain structures. So there is an optimum condition. You can get a very large width in terms of the grain. Yeah, you can get these coarse columnar grains. So this can be manipulated depending on the energy input you put in. Yeah.
Okay, thank you very much.
Thank you.
Are there any further questions? Okay, well then I think this concludes this afternoon's sessions. So again, a big thank you to all the speakers. I certainly enjoyed the talks, and I thought it was some very interesting topics discussed this afternoon. And yeah, I look forward to some more talks tomorrow. Thank you very much. Goodbye.
Thank you. Bye.
Bye. Thank you.
Thank you. Bye.
Bye.